So, some of these British signatures you will find it when you come to IISc campus and all that, including our main building, what you see here. All right. So, but after independence, you are kind of completely autonomous, and you have more than 40 departments, blah blah, all sort of things. I don't want to spend time on that actually. Then all of my work that you are going to, I mean, what you are going to see here today, I will take you through some of the research activities also. It is not going to be purely introductory. Okay. But having said that, the research problems that we work on is typically I will say application driven theory. It is not theory driven application. Okay. You get hold of some application, then try to apply something. It works very well. If it does not work, go back and see why it does not work, and then try to revise your theory, come back and apply, it should work actually that way. So, in that sense, we have been fortunate to work with a lot of these research funding agencies, and primarily the funding comes from this Defense R&D organization, DRDO, several labs of DRDO. Okay. ASL is responsible for ballistic missile, RCI, DRDL, Anurag, all sort of things. ARD, CARE, I mean many things there actually. So, different part of the project has come from different labs. And then we talk about ISRO as well, primarily from ISAC and VSSC. VSSC is launch vehicle, ISAC is after the launch vehicle job is over, the satellite job starts. Okay. So, that is where the ISAC comes into picture basically. Design and deployment of satellites both. Okay. Then you talk about a little bit funding from abroad, Air Force Research Lab from US. They have also some sort of unclassified way of supporting things and all that way. And obviously, some private aerospace industries as well. Okay. So, these are the things that have given me a lot of these projects, but projects come with problems actually, right. So, the problems are very good in the sense you get into the some insight of real world problems actually, okay, and try to contribute something more than double inverted pendulum or something like that actually, right. I mean, lot of the time we get stuck with the inverted pendulum business. Okay, so but beyond that, life is there. I mean, that's the message actually. Okay, all right. I have no derogation anywhere, but still. Okay. All right. So this is the thing that I am going to talk a little bit detail today about ISRO related issues. A particular problem of interest will be like soft landing on moon, so and then formation flying of satellites and things like that. Actually, we will talk about that as you go along. We'll also talk a little bit on this missile guidance before that, basically. Okay. And if you happen to come to my lab, and most of you, I mean, all of you are welcome to visit IISc any day, then this is what you see. I mean, our lab works on guidance and control of missiles. We also work on UAVs. We work on advanced aircrafts. We also work on satellite related issues, attitude control, formation flying, things like that. We are also interested in biomedical problems and process control. These are also like kind of feedback control system in some sense, as long as you talk about automatic drug delivery. That is what we worry about primarily. And then process control, all of you know basically. Okay. But if you happen to come there, you will see nothing. Okay. None of the things are there, other than a little bit of that and probably one of that or something. Okay. So all these things are there in your brain actually, inside the computer and in your brain. That's all. There is nothing called a physical system that we build and fly and things like that. But you get associated with all sort of programs, and the algorithms part is typically going to go to the flight computer basically. Okay. So that is what you are worried about, how to get the flight going and things like that. And acknowledgement without I mean not acknowledging students is not really good, and because many of the works are getting done through pioneering works of the community, I mean the group itself basically. Okay. So in that sense, I have been a little bit fortunate, starting from Mangal right there. Okay. And then we have got all sort of things we have actually flourished in their things actually wherever they. If you see this 4-5, first 4-5 have already become faculties. The next 2-3 are very well doing in DRDO, ISRO, things like that actually. So they are the one who has also given a lot of contribution to this what I am going to talk today basically. Okay. And this is not an exhaustive list, of course. I mean, lead another 1 or 2 slides if I just want to put everybody there actually. Want to do that. So what's the outline of the talk today? Generic overview of optimal control theory. That's what I am going to do it now. Okay. And it's supposed to be the most difficult lecture actually. Okay. Immediately after lunch in AC room. Immediately after a heavy lunch in AC room is a perfect recipe for sleeping actually, right? Okay. And that is then you bombard with a lot of math actually. So what you happen? Okay, you talk, I sleep. That's it. Okay. Right. All right. So that is, we'll try to do that. So get ready for doing a little bit of algebra yourself basically. Okay. That will give you some sort of insight basically. Lecture 2, after this we will talk about a particular approach that we talked about, model predictive static programming, all sort of things. That's the approach that I will talk about in some detail. Okay. Here I will talk about a variety of approaches, but then when I go to the lecture 2, I will talk a specific specific design technique in some detail, okay. And lecture 1 and 2 will be roughly theory. Okay. So, once you understand these two and implications and all, then we talk about the last one with lot of application problems basically. Okay. And all of these applications are related to aerospace. I don't know how many of you are aerospace people here, aerospace department. Okay. Those of you will connect, but the good part of aerospace is also very intuitive, right. Every day morning we see birds flying, right, at least mosquito flying. Okay, we see everything actually, right. So, everything happens in 3D, every day sun rises there, sunrises is so far away basically, right. Every night you see moons and stars, they are all intuitive basically. Okay. So, this is what happens there. So, just do not get afraid that okay, you do not know aerospace and all that, it does not require to be that exhaustive knowledge a priori basically. Okay. All right. So, with that motivation let us get started. We will see about some overview of optimal control design. So, of course, this is if you really want to talk in an exhaustive way, I need half a semester actually, okay. Half a semester. Okay, I do not want kind of distract you or kind of frighten you or something, but just have a glimpse of what is going on there actually, okay, some sort of feelings basically. So, so before that somebody can ask me why optimal control. Yeah, I know what is that, I know pole placement, I know feedback linearization, I know backstepping, I know adaptive control and all sort of things basically, right. So, why do you not talk about optimal control? What is the necessity there? Yeah. So, what is the summary? If you know optimal control, then you can think about solving variety of real life difficult problems. Okay. That is the first thing, and you will see some sort of an idea you will get as you go along basically. Okay. So, a variety of difficult optimal control problems, a difficult control design problem, okay, can be formulated in the framework of optimal control, which are all other design, I seriously claim all other design techniques do not give you the platform. Okay. It is a very strong claim by the way, and I am ready to defend that, okay. Because your toolbox is suddenly become much more than just a screwdriver actually. Okay. If you do not stability theory, I will put that okay, some sort of set of screwdrivers, right, okay, small one, big one, whatever it is, but all screwdrivers only. But if you really want to do something better, you need a variety of toolboxes, right. You need some hammer, you need some spanner, you need some screw, I mean all sort of things actually there. So, those kind of things will come to you when you know some sort of optimal control theory. The reason behind that I will tell you actually why so. Okay. The reason is this, primary reason is this one actually if you ask me. Okay. This is one platform where you actually can talk about enforcing state and control bounds. Okay. All other things we never bother about that, right. All that you talked about is okay, if I in the process of my adaptation, if my control signal goes much beyond than what I can implement, all that I can do is hold the control. Okay. The control bound issues were never talked about, right. And similarly state bounds also. Suppose you want to land and I mean just turn an aircraft, in the process it just goes and crosses actually, right. Do you want that? Obviously not, right. These are unbounded problems and all that. So, you while you do a turning, your all other states will remain meaningfully bounded, just not bounded, okay, by the way, right. Just if you just simply tell bounded as does not attract me actually, right. It has to be talked meaningfully bounded basically. What is the meaningful bound? Your altitude take height actually, right. So, height should never become 0, it is a meaningful bound actually, right. Any negative value if it is bounded, what is the point actually, my vehicle is already crossed basically. So, anyway, so this is the reason the state and control bounds can be incorporated explicitly, and means you pose the problem, you demand a priori, these are my bounds and give me a solution within the bound actually, all right. Number 3, okay, in the process of that when you talk about state bound, you are not talking only inequality bound. Inequality is norm of x will be less than equal to some value and all that, right, that is the inequality bound. You are also talking about non-honoromic constraint. What is that? The state equation itself, right. If you talk about a solution, the state equation itself you have to worry about actually, right. What is the process capability or the plant capability? Okay. If you talk about dynamic inversion, feedback linearization or even this adaptive control, all that, what is that feedback linearization does? A desired error dynamics. Okay. You put a desired error dynamics and somehow try to enforce that based on the system dynamics, right. Whether the system dynamics is capable of doing that or not, that is the least bother for you at that point of time. If it is not, then go back and tune your design and come back and experiment, that is what you do actually, right. But here you talk about wait a second, I have got a Maruti 800 or a BMW or a Mercedes, I know it. Okay. If I know that kind of a thing, then I better choose my conditions like that actually, right. But the system dynamics is all about that basically, right. Whether you know your vehicle a priori, you know your robot a priori, you know your process plant a priori, and how they operate you know that, that is nothing but system dynamics. So, system dynamics you implement it as part of the path equality path constraint. Okay. So, non-holonomic constraints will be guaranteed to satisfy actually that way. Okay. Then on top of that, this is already a good advantage, right. And optimal control theory is very powerful because of constraint issues, just believe me actually. I mean that's the bottom line actually. But in the process, if I get something extra, why not actually, okay. Right. In the process, right, I go for my lunch actually, all of you go for, we are hungry, right, you went to lunch, you got it, right, all your food and everything. If gulab jamun was not there, fine, no problem, right, isn't it? I mean, your hunger is gone. But if it is there, the food becomes even more tasty actually, right. Right. All right. So, something similar actually, right. It's just not only that, I mean your entire lunch is over, but still you can talk about more than that. What is that? The optimality issues, right. In what sense my controller is optimal? What is optimal? Either minimum or maximum. You talk about profit maximization, you talk about loss minimization, okay, either way basically. Okay. So, essentially what you do most of the time, we worry about control solutions with minimum control effort, because remember all the thing that you have in your hand as a control designer is that little you fellow, right, somewhere sitting there. Okay. That you is the one you are going to design, or you are going to come up with a formula, number or whatever it is actually. Okay. So, that you is next time I say controller is not everything, you need to put that in the actuator basically, right. So, that means your control that you want to implement has a penalty to pay, right. So, every workshop is not like that free, right. Anytime you want to attend a workshop, you have to pay money also. Okay, that is right. Yes or no? Most of the time. So, the thing is you can compute a very good controller, but implementation of that requires energy, right, some form of energy. And in flight vehicles typically it is supplied from batteries basically, right, onboard batteries, which is limited. So, you do not want to consume energy just like that basically. Right? So, this u and u dot and things like that, those are very good quantities to think about minimizing. So, if I talk about minimum control effort, I can probably sustain my flight vehicle for a longer time. Okay. Satellites for example, they get exhausted because your RCS fuel gets burnt out actually. Okay. So, if you just talk about minimum RCS like a small gas, little bit of gas or something. Okay. If you minimize, you can operate the satellite for a longer duration of time, as obvious as that basically, right. So, that is why minimum control efforts are very good to have it actually. Okay. So, you can talk about that, you can talk about variety of advantages such as minimum cost, maximum efficiency, all sort of things you can talk about, as long as you construct cost function, then that cost function will have meaningful to you, something like that. Okay. And also these trajectory planning issues you can do that on board. Okay. In other words, if you, in addition to this formulation, okay, all this formulation, you can also come up with a very fast solution strategy. Okay. Your algorithm becomes very fast, then you actually can think of doing all these optimization on board online basically. And that is what I am going to talk about next class and all that actually. How do you do fast computation? That is what it is. All right. So far so good, motivation part. Okay. So, this particular to a platform gives you a very good I mean kind of framework for which you can talk about a variety of difficult problems basically. Okay. You can ensure a solution which will satisfy constraints, inequality, equality both. It can also satisfy final boundary points, initial boundary points as well. Like if you talk about an aircraft coming landing, I mean going from Lucknow to Delhi, then Lucknow should be the starting point, Delhi should be the ending point, right. So, also starting final and end points also you can dictate. Initial time, final time also you can dictate. Okay. So, you can see the enormous amount of freedom that you have. Initial time, initial condition, final condition, path constraint, system dynamic constraint, optimality issues, all sort of things I can talk about actually. Okay. That is why I told this toolbox suddenly becomes much richer basically. Okay. All right, all of you are control systems, right? You have seen this diagram. Who has not seen this diagram? Anybody claims that you have not seen this diagram? Everybody. Okay. Now, I will pick up somebody. Okay. Okay. And you tell me what is R of S? What is R of S? You see all these things, right? And the last lecture we talked a lot of things about R of S, R of S, R of T, all sort of things, right? What is R of S? Tell louder, we do not have too much of time, just participate, feel free to participate, quicker also, louder and quicker. Reference input. Give an example of reference input. Step input, ramp input, parabolic input, these are the things that are taught in the book. Okay. Now you go, where do you, I mean, do you stay in the hostel or what do you, any day scholar here? You are the day scholar, right? How did you come? Cycle or bike or what is it? Huh? Cycle. So go out after the lecture and give a step command. What will you do? Step command, no? What will you do? Your cycle you take out and all that you are constrained is give a step command. What will happen? Will you ever go to hostel? No, you will just keep on turning there only, that is all actually, right? Okay. So step commands, RAM commands and all that are really not good things. Now the question is, nobody asks that in the class and no teacher tells also basically, right. So forever we get locked in the mindset that R of S is nothing but step input, ramp input, all sort of things basically. This is not really true. And in the frequency spectrum, what do you do? Frequency analysis, these are nothing but sinusoidal signals. Suddenly you forget step input and go to sinusoid, which is very good actually something. But these have justifications as well. What is the justification? One comes from Fourier series, the other comes from Taylor series. If you take step input, ramp input, all that, they come from Taylor series. Sinusoidal things come from Fourier series. So any signal you can decompose that like that actually. In other words, for a real good operation of the plant, all that you need is a real good R of T, right. Once R of T is given to you, you have got toolboxes ready, right. I can do adaptive control, all sort of things, feedback linearization or backstepping or whatever it is actually, okay? Or if simple pole placement and scheduling, all sort of things. Once R of T is given to me, my output can track that R of T, right. That toolbox is there with us. Now the question is, what is R of T? Okay. That comes from meaningful optimization process, right. If you really operate a chemical plant, then you don't want to produce too much because they may get obsolete. You don't want to produce too less, then they see your demand is high and you are not able to supply. So there is just in time concept sort of thing, right, lot of things basically that way. So you have to talk about this R of T generation is where your vitamin M lies, okay, right, your vitamin M, money, okay, okay, all your vitamin M is there in the R of T. Basically, now the question is, how do you generate that R of T, meeting all my requirements basically, okay. So that is where you think about, well, wait a second, can I really do that or not? Okay, because this R of T should be meaningful to this plant, right? It should not be useless R of T basically. There is certain objective that this plant has to do, and for that I have to supply this R of T, and that is over a period of time I want to see my maximization, minimization, constraint satisfaction, all sort of things basically. So what is the idea there? You talk about, can you put this? Okay, this was not there, right? Now think about putting this. Okay. So you put some sort of little bit of reference signal you use, and then put some mission objectives also, but what you expect from the plant, okay, and then you do some sort of optimization there, and then you feedback generate that R of T, okay, and that is where this optimization comes in picture. And because it's a dynamic system, everything changes with time and things like that, you talk about dynamic optimization. Okay, then many times you will see later this is also called dynamic programming. Okay, programming does not necessarily mean Fortran or C programming, nothing like that. Okay, programming means optimization. Second World War time, this generals and all, they were using this word programming, how to optimize their troops and all that actually that way. Okay, so that when you see this programming word, it is nothing but optimization. So dynamic programming or dynamic optimization essentially. Okay, clear? What is optimal control? Largely we are worried about how to generate an R of T in a good way, all right. And information from that can come from the plant itself, plant output, as well as they are very important mission objectives basically. Okay, if you can do that in the outer loop, you can do a bigger job, you can also do a smaller job. I mean this is actually gives you some sort of outer loop, and that is inner loop. Outer loop can be optimal control, inner loop can be stabilizing control, fine, fair enough. But somebody can also think about, remember, optimization is a superset, stabilization is a subset in some sense, okay, right? Because any control that is optimal is also stable. Okay. So if you can do that, you can also generate a subset of that and then tell, okay, I can do this also. Okay. And this is nothing but what you standard famous optimal control you see there, which is called linear quadratic regulator. That's the philosophy that operates there, asymptotic stability and all that, inner loop. That outer loop will typically operate on finite time stability, finite time problem formulation basically. All right, before going to math, a little bit tribute to the pioneers. I can see all the way it can trace it back to Newton. Okay. What the Newton concept? Steepest descent method, right? How many of you heard about it? Steepest descent method. Most of you must have heard about it, right? So what is the idea there? in a state space or wherever Rn, if I am there somewhere, then the gradient vector gives you the maximum ascent direction. So, the negative of that will give you the descent direction. So, if you want to maximize a function, go in the gradient direction, and minimize the function, go in the negative direction. But the thing is, they are very local. The moment you go somewhere, the direction changes. So, keep on doing that, and then things like that actually, right. So, that is all that Newton's method actually, and he is a great mathematician. He has given us several physical laws as well, but he is not a physicist basically, he is basically a mathematician. But see, the physics and math, if you talk together, then a lot of nice things happen actually. Okay. So, that is what happens there. But then Newton's contemporary was not sitting idle, and there was another line of thought. Starting, you can trace it back to Bernoulli actually. Okay. In fact, Bernoulli and Newton's were contemporaries and kind of not going well together. You can see the history and all that. They were writing some sort of a kind of rivalry sort of thing basically, okay, which is expected in a professional world, right. You always get used to that actually. But if you see the real optimal control theory, they started from Euler-Lagrange point of view. Okay. You will see real equations actually, very standard. The calculus of variation was formalized through this Lagrange primarily, okay, not even Euler. But before Lagrange, Euler gave some sort of a discretized form. Okay. Lagrange gave a continuous form actually. Okay. But then there is also known as if you just take discrete form and take limit delta t tends to 0, then you will end up with continuous form. Okay. So, that is why it is called this EL form all the time actually, Euler Lagrange actually. Okay. So, all these things happened when 10 generations back at least. Okay. You can see that it is not a type of mistake. Okay. All happens in 1700 something, 1731, 1734 also things like that too actually. Okay. Then people tell, okay, you can see that, and as you can work out a few problems, very simple problem. It will take some 10 pages of algebra. Okay. Optimal control it requires a lot of algebra basically. Okay. So, in other words, there was all sort of mathematical heavy sort of thing. You just do it, at the end of the day, you just go nowhere actually, right, because there is a small tiny problem that you are talking about, for which you require so much of algebra. There were no computers, remember that, no slide rule. Okay. Everything has to be done in a hand calculations actually. So, numerical things were simply ruled out. Okay. So, this field had a nice natural death. It just died out for 100 years actually. Then after 200 years, one person single handedly revived this field actually, one person by the way. Okay. And that person happens to be this fellow. Okay. Okay. And you can see this a little bit carefully to his eyes basically. What do you see? Eyes. Do you see something? Or your eyes are closed after the lunch? What do you see in his eyes? Blind. Okay. Actually, he is not born blind, he was blind from some sort of explosive experiments and all that actually. A blind fellow doing a hell amount of math, and then that too completely reviving a mathematical field is, I mean, you can imagine what is there actually. And his mother was his input output sort of coordinator basically. So, she used to read, the fellow has to understand, and he will tell, the mother has to write, also things, that kind of thing. And to revive this field, he did not sleep for 3 days it seems. Okay. And so, while he was almost there like that, 3 days he did not sleep before getting that. Once he got it, then slept. That's the story actually. Okay. Okay. That is what the real scientist researchers are all about actually. When you just go there, you just go there. That's how it is actually. Anyway, so that is the story. Then it comes to modern days. It is a lot of this. Bellman is credited for this dynamic programming sort of thing, and Kalman, who actually passed away 2 months back. Kalman passed away in July basically. Okay. So, he is the pioneer thing for this LQ theory, linear quadratic theory, and both control as well as estimation actually. So, these are some of the figures, and I do not tell that everything exhaustive and all that there. But interestingly, very interesting, I just came to know that about not even a month back actually. If you trace back, how many of you are interested in, all of you are doing PhDs? PhD, masters, this, that and all, how many of you are doing PhD? Okay. Okay, who is your grand guide? Okay, tell me. No, I am asking you. Guide's guide.
My guide.
Who is your guide? Everybody knows, right? You ask me who is your guide's guide, maybe. Okay, who is his guide? Okay. Well, there is a family tree sort of thing, right? Your father, grandfather, grand-grandfather, all sort of thing. You can also trace back these days to your guide of some 10 generational guides actually. Okay. So, if you can do that, and somebody pointed it out, that I belong somewhere and it starts from somewhere. Okay. All right. All right. There are two trees out here. You can trace it back to Euler-Lagrange or you can trace it to Gauss also, basically. Okay. All right. So, this is just a kind of coincidental or whatever you can say that way, but this is what happens. I mean, if there are websites these days where you can go there and find out, basically. Okay. You just give one fellow name who has his PhD guide, then you put that fellow's name who has his PhD guide, like that. Actually, okay. Okay. And this is in front of you. I am going to share with you. I should get that. Okay. All right. Now let's come back to serious things, basically. Okay. So, what is optimal control? An optimal control problem consists of 3-4 components. Okay. One is the performance index that needs to be optimized. Optimized means either minimum or maximized. Second is the boundary conditions, either initial and final. That can be either hard constraint or soft constraint. So, suppose I throw the ball somewhere, right? I throw some sort of a, see this, this golf game, right? Golf game. What does the fellow do initially? Is there somewhere? Okay, he has to just put it, right? So, he has to put not in the opposite direction of the hole, so somewhat in the same direction of the hole, basically, right? So, as long as it comes closer to the hole, his objective is done. Okay. From far away, you cannot aim to have a very tight one shot, it will go to the hole. It does not happen that way. Okay. But when you come closer to the hole, then the next one is you have to put it in the hole, then only you will win the game, otherwise not, actually, right? So, you are seeing when you put that exactly on the hole, that is a hard constraint problem. But when you are far away, you are somewhere close to that. You do not care about what is where you fall and all that. As long as it is the ball is ensured, you are fine, actually. And that is why it is executable. Otherwise, if you just put a condition that all golf winners have to win it in single shot, no winners. Right? It is an impossible job, actually, that way. And remember, golf balls is also like single point control, right? On the way, on the fly, you cannot control. You can only control while hitting it, right? It is a boundary control problem. One instant only you got the control action, and that has to be so good that it has to directly fall on the hole, actually. So, it's kind of impossible, actually. Okay? So, that is the problem difference between hard constraint and soft constraint. Okay, understood? There are problems like that. Now, if you want to go there, explore a balloon or something, like flying balloons are still available. You want to just use it and go somewhere, and you put it as a hard constraint, it becomes very difficult, actually. Okay. But if you talk about a missile guidance problem, without hard constraint does not make sense. I want to fall on the terrorist head, I will fall on the terrorist head, not on the neighbor's head. Right? If my missile goes and falls on the neighbor's head, terrorist is more happy, right? You have done his job, actually. Right? Right? You have done his job. Okay. So, that is not acceptable. So, sometimes you see where is it acceptable, where is not. Putting a hard constraint, do not get tempted to. If you put a hard constraint, you will get much better solution, but the penalty for that is heavy also. Okay. But it is possible, certainly. Both the versions are possible. Second thing, the next thing is path constraint. As I told, system dynamics constraints, state constraints and control constraints. This is equality, these two are inequality. These two are bound values, T naught x naught and T f x f. Okay. So, all sort of things you can do that way. Okay. Mathematically speaking, and now you have to start writing. Now you have to start writing, all of you. Okay. Otherwise, you will sleep. Okay. Do not write all the English there, English is not required. All that you have to do is, there is a system dynamics, you write x dot equal to f of x u, and this performance index, only dynamics and index you write it, you will need that next step. You have got a system dynamics, x dot equal to f of x u, the T1 you can suppress if you want to. So, you have autonomous, non-autonomous is fine. Okay. So, you have got a system dynamics and you want to optimize a cost functions in this form, you have got initial conditions known to you and you have to find out this ut, right. In other words, you have to find out this u of t from T naught to T f, which will satisfy the system dynamics constraint and including initial condition, and at the same time it has to optimize this cost function. Clear? Okay. All right. So, find an admissible control. The moment you word introduce this word admissible, that means it has to satisfy all sort of constraints. Okay. So, find an admissible control for this particular nonlinear system. There is no linearity here, you know that, and there is no control affine, there is no CISO, nothing. It is all MIMO, nonlinear, everything there. Okay. and then you talk about it will follow an admissible trajectory which will optimize this performance index, okay, and then it will satisfy the appropriate boundary condition also. Clear? So far so good. Now, how does it happen? Now, the question here is, most of the time you will be given with the system dynamics, right? You have got a robot or vehicle or power plant or whatever it is, motor or whatever it is, the system dynamics is typically given to you, you do not have a choice. Boundary conditions come from performance objective, you do not have a choice either. Most of the time you start with this initial condition, go to that final condition, that kind of thing. So, what is left out? Constraint values are also given to you. What is left out? Left out is typically the problem formulation, okay, and problem formulation includes both these constraints as well as cost function. So, you have to select a cost function yourself, okay. The rest of the things will be given to you, right? Given a cost function, how do you optimize it with respect to all these things, that will talk. But to begin with, in any problem you want to formulate, see you have got these tuning parameters, right, control tuning parameters, all sort of thing. So, the tuning parameters will typically will be in the form of selecting a cost function and then putting appropriate boundary conditions, okay. You have to select a boundary, you have to select a cost function, that is meaningful, and you have to pose the boundary condition, that those two things are on your hand actually, those are nothing but the tuning basically. Now, the question is, okay, if you talk about something of this form, what you see here, there is an integral form, integral component, exclusively there is a final component, right. There is a final component, at t equal to Tf there is something, and T naught to Tf there is something else, okay. This is path dependent and it is terminal point dependent, okay. Now keep that, you have all written down, right, written down this. Now, tell me what should be phi and what should be L for a minimum time problem. You have written down, right, just look at this form and tell what is phi and what is L. You want to solve a problem minimum time actually, right. What should be phi, what should be L?
Sir, I have a question. That integration already includes the final point, even though it is.
It doesn't. It doesn't. No. Just before it, Tf minus epsilon, it will stop. Okay. That's the implication basically. Anyway, so just tell me what is phi and what is L for a minimum time problem. Phi is 1, L is 1, phi is 0. If you put phi 0, L is 1, what you get? J is nothing but Tf minus T0, execution time, right. So, that becomes minimum time problem. So, what if there is a minimum control effort problem? I just want to have do my objective in a minimum control effort sense. All that I have to put is integral u square is a multivariable sense, it should be u transpose u, okay. And if you weigh out different things, in other words it is R1 U1 square plus R2 U2 square like that, then you introduce a weighting function also u transpose RU basically, okay. So, it happens like that basically. So, this is a minimum time problem, for phi is 0, L is 1, minimum control effort you take it that way, and typically half is introduced for algebra simplicity. You need to take all sort of derivatives, and quadratic terms if you take derivative 2 will cancel out and all that, it doesn't hurt you also. If there is a function you want to minimize and half of the function you want to minimize, the minimum point happens at the same point actually, right. That is the whole concept actually, okay. There is a function, okay, any x or whatever you take it, there is a function of this form and half of the function is this form, right, exactly half or something. So, the where optimization, where does it happen? It happens at the same point only, that is what you mean. So, introducing the half term does not really hurt your algebra. Objective are not hurt, algebra simplicity is brought in actually, okay. Alright, so this is what it is, and suppose you want to talk about, well, what do I do with minimum control effort? It does not do my job, okay. I have to do my job first actually, right. So, think of some sort of a, let us say helicopter hovering problem. There is some problem there, somewhere some what is that, some rescue mission or something is there, and helicopter has to go and then put the rope, right, and that fellow has to grab the rope and you bring it up actually that way. So, then the helicopter has to stay there, remember that it has to hover there. So, that means your x has to be close to C is the desired coordinate, let us say, okay. So, the deviation from C should be minimized first thing first, and then while I do that I do not want to put too much of control effort. So, that is a combination of your minimum error and minimum control, got it. So, these are the ways, this form that you talked about, if you see this, what is your phi is 0 and L is this one, okay. Similarly, you talk about, well, I go from here to there and hang around, just talk about helicopter starting from here and going to the point and then hang around there. Okay. So, this is so you visualize the problem and accordingly select a cost function, that is what it is. So, if it is path dependent, put it inside the integral. If it is only terminal point dependent, then put it outside the integral. Okay. So, T0 to Tf and things like that way. Everybody clear? This is just some 2-3 examples, but depending on your problem objective, you have to select what is your cost function and you have to select your boundary condition especially. You want to put that as a hard constraint problem or soft constraint problem. Okay. Next one, you want to do the minimum deviation of state around the origin, you put it this way, standard quadratic function, and as I told, you want to go there with minimum control effort, but hang around there. Okay. At that point of time, control effort is not very critical. I have already gone there. So, during the path, my helicopter control effort should be minimum, and after I reach my destination, all that I have to do is hang around there basically. So, in the entire path, I have to go that point, I should not go somewhere else, right. There is a problem in that direction, I have to go that direction basically. My vehicle should not go that direction basically, right. So, that this term will guarantee that, because your xf minus xe, when t goes to tf, your x should go to, xf should go to c. Okay. So, this term will guarantee that basically, the direction of movement and all that. Okay. All right. So, these are some examples basically. Okay. Now, the question is, okay, all these things are can be thought about some sort of a path optimization, and that is where this concept of functionality comes actually. How many of you heard about this term functional? Functional. Okay. How many of you heard this term function? Function. Everybody actually. Okay. So, functional is kind of a generalization, it is nothing great actually. It is a function of a function, that is as simple as that actually. Say like Lie derivative sort of thing yesterday you talked about, right. Like that actually. Okay. So, talk about functional something. Okay. But the condition is there is something called a independent variable. Okay. The independent variable you cannot vary, and what is the natural choice of independent variable? Clock fellow, right. It does not stop, it does not listen to you at all, you have to listen to it. Right, the time basically, right, it does not stop, I mean it just evolved basically. Okay. So, in every problem there is something called a independent variable, it does not with respect to that you have to optimize, and a very natural way of looking at that is time and physical time, that is what it means. Your missile has to fire and that fire is T0, 0. When my T equal to Tf, let us say 10 minutes later I have to destroy the target. Okay. That becomes your Tf. So, that is naturally time is a natural choice of independent variable. What is good about time variable? It is both continuous and monotonic. Okay. What is monotonic by the way? Either keeps on increasing or keeps on decreasing, that is monotonic, but time is always increasing in some that sense basically. Okay. But it can also be posed as a decreasing problem, right. We always celebrate our birthday, right. This is a good thing to celebrate or bad thing? Birthday. So, you always count your T0, your birth date. Why whatever your final day, you are approaching this, right. There is a final day for all of us, right. So, you always count birthday, okay, T0. What about counting that day? Okay. Then your time is getting squeezed. But either way it is monotonic, right. Either it is increasing or decreasing, it is continuous and monotonic both. Okay. So, birthday is a good thing to celebrate, I do not know. All right. All right. So, now the question here is, all right. So, there is something that evolves actually, time evolves, and with respect to time something changes basically, right. So, if something changes, then I should be able to tell which is my good path basically, right. This is actually a function of time. Okay. Now, functional will be a function of x, remember that, and these are all functionals basically, right. J is a function of x, but x is a function of time, and time is independent variable. Okay. So, with respect to time, I claim that my x star, you see the star notation, my x star is optimum. What does that mean? Okay. It means that if I have got an optimum trajectory x star of t, which is the dotted line, let us say, I go from here to there in that way, and then I get my minimum cost. Cost function is optimized. All that it means is, if I take any other path, my cost function is not optimized. Mathematical people are very nice actually, right. We just put a word not. Okay. Right. Okay. You take this path, it is optimal. You take any other path around that, it is non-optimal. as simple as that basically. Okay. Now, the question is how can I derive a condition based on that basically, that is what it is. Now, if you see a difference between them, okay, the difference between dotted and solid line, and you simply take the difference is also continuous, by the way, this is continuous, that is continuous, difference is also continuous. So, this difference is what you call as variation. Okay. If it is just a function, you call it deviation, is a variation because it is time dependent actually. Okay. So, this is called, it is not variation, it is not deviation, it is variation. Okay. So, that is called variational calculus because of that. Okay. Calculus of variations or variational calculus like that actually. Okay. So, that is the concept. All right, everybody clear? All right. Now, necessary condition tells you that okay, if I got x star which is optimum, then this condition first variation has to be 0. I mean again all detailed time I do not have. So, some of these things you have to just take it on face value probably. So, the necessary condition from calculus of variation tells you that if I got a path optimal control problem like that, then the first thing that I look forward to is necessary condition optimality, which tells you that first variation should be 0. It is almost very similar to static optimization problem. You just expand it using Taylor series and claim that okay, sign dependency should not be there, blah blah all that actually. Okay. So, in that sense you can very easily prove that first variation has to be 0, and this is what is heavily used by the way. Okay. And then you tell now sufficiency condition, then second variation has to be either positive or negative. So, these are all this positive definiteness, negative definiteness like that actually. Okay. Like Taylor series, any continuous function you can expand it using Taylor series. Very similar things you can do it here as well, function of function basically. Okay. And then you can do about first variation, second variation like that actually. Okay. All that, remember that is not a when you talk about deviation, it is a point evaluation, right. One pointer what is happening, it is a variation what is happening over a period of time actually. Something changes and what happens. All right. Now, there is another fundamental lemma, it is almost like a Barber-Lutz lemma, I can say that way, okay, in optimal control. Okay. In the Barber-Lutz lemma happens to be a backbone of adaptive control, right. Now, here this particular fundamental idea there is no name actually. Okay. I mean way back 200, 300 years back, people did not worry about their names. But anyway, so that is coming back. What it tells you is, if for I mean just forget about the math jargon here. What it tells you is, if this condition holds good for all possible variation delta x, then this g of t should be 0. Okay, do not read it. If you read it, you will get confused actually. Okay. Just look at the condition. If this condition holds good for all possible variations like this, right? There are infinite variations around the dotted line, right? For all possible variation, if it happens like that, then the only way it can happen is the coefficient should be identically 0 throughout the interval. Okay. It is not 0.0, it is just 0 throughout the interval actually. Okay. It is very easy to see that if this happens, then this happens, right. If g of t is 0, then this is obviously 0. Okay. But what it tells you is reverse way. It tells you if this condition holds good for all possible variations, then the only way it can happen is the coefficient should vanish actually. Okay. Otherwise, I mean we will be stuck actually. This condition is heavily used. This is what is shown in a scalar sense, but it can be generalized to vector sense also basically. Okay. Now, come back to where we started. We have all written down, right? All of you have written down this. Now, let us try applying that. Okay. So, what we do? We know there should be first variation and first variation should go to 0. That is a necessary condition of optimality. So, we have, and then there is one more missing thing here is what your Lagrange idea basically primarily. So, this Lagrange multiplier, how many of you have seen that? There is something called Lagrange multiplier in static optimization. Okay. So, Lagrange contribution again, what it tells is dualization of the problem. You dualize the problem, in other words, do not see the problem in n dimensions, so we see the problem in 2n dimension. Okay. If I have to give an invitation, I have to invite a family only. You and your spouse both are welcome. That is what you normally do, right? Right? If you give an invitation to somebody, do you tell only you are invited, your spouse is not? I mean, it is not possible, right? So, see always together sort of thing. So, it is called dualization problem basically. Okay. So, that you talk about that and then problem certain simplicity starts appearing actually. If you dualize the problem and then simplicity starts coming, I do not want to go into detail through that, but what it tells you is this equality constraint part especially. Okay. So, remember this cost function talks about entire T naught to Tf, but the entire T naught to Tf you have got some constraint to worry about, equality constraint. Okay. So, this entire problem what is called constraint optimization can be converted to free optimization problem using the concept of dualization. Okay. So, then in other words, every point of time, let me visualize some lambda of t, some other variable lambda of t, which operates, which along with this will operate actually. See, this is not, is no more called as Lagrange multiplier, now it is called as co-state actually, okay, state and co-state. Okay. That is also a function of time basically. Okay. So, if I talk about x of t with respect to x of t in state space, I have got lambda of t in dual space. Okay. For each x of t, I have got a lambda of t, and they operate in such a manner that this constraint optimization problem can be converted to a free optimization problem. Essentially, that is the bottom line actually. Okay. So, that means let us construct that j bar, that is augmented cost function. This is your j bar. Now, you can start dropping these arguments and all that. This within bracket does not make sense. Write j bar using this and this. So, what you do? You write it as equal to 0 first, x dot minus f of x or whatever, right? You write this fellow okay, equal to this 0. So, in other words, f of f minus x dot equal to 0, right? That happens for all time. So, what you do? Your j should contain phi is a point value, right? Phi is tf only. So, that phi you keep it phi, and then this within the integral t0 to tf, you have already got L. Okay? You already got L, and every point of time you are getting this equation satisfied, right? So, all that you have to do is lambda transpose f minus x dot, okay, dt. So, somebody can also see that this is nothing but 0, right? F minus x dot is 0, right? So, this is also 0 basically. So, you are not really perturbing that actually. Okay. How many of you know linear algebra, by the way? Linear algebra. Don't cheat me. Okay, all of you know linear algebra, right? Yes or no? There is something called null space. What is null space? Null space, right? You write some vector in the null space, even if you multiply with the matrix, you will get 0 only basically, right? That's the concept of null space basically. So, similar something, so you can visualize something similar. Okay? All that there is a 0, but I will add it to that. So, the j bar is not really different from j, but it embeds this fellow in a, I am looking at the problem in 2n dimension now, right? Earlier the j operates in x and u only, and remember u is a subset of, u operates in which state? By the state space only, right? If you want a feedback control, u is a function of state, so u operates in state space only basically. Okay. So, this entire j operates in state space in some sense, but now the moment you introduce lambda, j bar operates in state space as well as dual space, 2n space actually. Okay. That is the concept basically. Okay. Even though the value is same, there are certain dummy variables, redundant variables, you can say that way, right? You know this chemical people, I mean any of you from chemical engineering? Nothing. All of you know what is catalyst, right? What is catalyst? It helps you getting a product, but after the product is on, okay, see you later. Okay, right? I don't worry about that basically, right? Like lot of times we end up putting chilies in curries basically, right? How many of you eat chilies? You can eat. Oh, okay. No, okay, you can eat. Then you don't belong to this class. Okay, but most of the time people just throw it. Okay, but you extract whatever is needed in the process, right? Then only your curry becomes tasty or whatever. Okay. All right. So that kind of a thing you can think about. So essentially, j bar is nothing but that. Okay. Once you have j bar, now for convenience sake, this is what Pontryagin suggested. It's a Hamiltonian formulation, blah blah all that. Before that, it was all EL equations basically. Now you suggest you write this something called Hamiltonian as this L plus lambda transpose, this part. Okay, it doesn't contain derivative, right? This fellow contains derivative. There's a derivative free terms. You write it. Start writing now. So derivative free things you derive as Hamiltonian H. Okay. So now H is a function of what and what and what? H is a function of state, control, co-state, all three. Right? Lambda transpose is there, no? Okay. By the way, remember all this, all the way whatever we are talking about, this J ultimately is a scalar. J is not a vector, no matter what actually. Problem can be n dimension, but J is scalar. We are not talking about multi-objective optimization. Okay. There may be conflict of optimization actually, right? So it is all single objective optimization. There is something called multi-objective optimization, there is something called multimodal optimization. How many of you know that term, multimodal? It is good to know that, some of that. What is multimodal? You heard that term, then tell, what is multimodal? Okay. For the same optimization problem, we may have multiple solutions. Okay, nonlinear problem, right? If you have got several optimum points, that is a multimodal problem. Okay. But if you have got two different optimization problems, the J1, J2 like that, that is a multi-objective formulation basically. There are two different things basically. Okay. So, here we are talking about multi-objective for sure, and multimodal will rule out numerical things and all that. Okay. The way you select this quadratic cost function, it will have only one objective, right, one minimum. So, that minimum happens to be global actually. So, there is no other things and all that way. Alright, so we will talk about that and then come back to this. This is Hamiltonian, right. So, what was the necessary, our Barber-Lett lemma equivalent sort of thing? First variation should be 0. Okay. So, now you analyze the first variation of J bar and consider this operation as something like regular calculus operation. Okay. It is very similar, results are there. It is like integral of variation is variation of integral, derivative of variation is variation of derivative, all these are there basically. Okay. Just consider this delta fellow some sort of a calculus operation, okay, with a pinch of salt of course. Okay. But similar equivalents are available basically. Okay. If you talk about variation of J bar, it will satisfy what is the derivative integral behavior, I mean the properties of derivative or integral operator. What is first property? Derivative or integral, what is the first property? Tell louder, I have got a hearing problem, so tell louder. Huh? Linear. So, these operations are linear. So, you talk about linearity straight there, right, there is a plus sign, so I will put this plus that is a linear. What is the next property? Variation of integral is integral of variation. So, that means this variation can be pushed inside. Okay. Once you push inside, again it is linear. So, I can take variation of the Hamiltonian and variation of that, and this is like derivative. So, that like derivative, I mean this variation of these two terms is like dy dx of f of x into g of x, that kind of formula basically, right. So, you do that, do that yourself now. Okay. Do this algebra yourself. Somebody is asking some question, by the way. Ask some. Huh?
Here also we are handling two different objectives, like
no.
Suppose control effort and
It's okay, two different things, but J is scalar. So, different weightage are given, there are two different factors, but ultimately they are combined to the one scale. In when multi-objective functions are typically done that way only. Even if you have J1, J2, you put some alpha 1 J1 plus alpha 2 J2 like
so that is a vector.
Yeah, but you do not see, you can interpret that way. So, if you can split it into J1, J2, you can think of that way. Okay. But ultimately, we will talk that is a non-conflicting. Multi-objective will be typically conflicting. Okay. All right, everybody done? Then expand this actually. What you have? First variation of Hamiltonian minus first variation of these two terms. So, these two terms, what will satisfy? Variation of lambda transpose x dot minus lambda transpose times variation of x dot. Up to that is done. All right. So, this is where you will end up with, right. Now, let us see term by term actually. Okay. This is almost like Lie derivative sort of thing what we talked yesterday basically. So, you have got this variation of phi is possible by variation of xf, no. Phi is a function of what? Phi is a function of xf only. Remember Tf there is no variation, right. You cannot wish to change time. Okay. You can only change the states basically. Okay. So, phi can change with the variation of xf. So, this delta phi what you see here, it can be written something like this. Okay. Because phi is a function of xf. Similarly, Hamiltonian is a function of what and what and what? Hamiltonian is a function of state, control and co-state. So, variation of Hamiltonian is three terms like that. Okay. First term, second term, third term. Okay. Everybody clear? You have to keep writing by the way. Okay. All right. What you can do for this, by the way, these two terms are over, right. Now, you to keep this term as it is, we don't deal, because variation happens in lambda, we do not worry about that, but variation of x dot. So far we have not talked about that, right. We know x dot is f of x u, but variation of x dot, what form it happens and all we do not know actually. So, what you do here is okay, keep that integral term as it is. This integral is also linear operator, right. This integral means this integral minus this integral minus this integral. So, you go to the last one and start analyzing the last one, and the last one happens to be something like that. When you see some term like this, what do you do? When you see some term like that, what do you do? What comes to your mind? If you see some term, integration by parts, right. So, you do integration by parts, do it, do it. Why not one more slide? Why not actually? Just do it. Okay. All that is going on here is integration by parts actually. There is no point in explaining. I mean, it's self-explanatory, right? Because I see it and then start. I mean, if you have got some question, you can ask me. Okay, this is integral of this term. So, derivative integral will go. You just simply evaluate at t naught x naught and t f x f, and then second term is integral of the first term. Sorry, derivative of the first term times integral of the second term. So, integral is that, derivative will remain actually. Okay. All right. Yes or no? Okay. Well, I am not going to give the slides, so just keep on writing. Okay. All right. All right. So, then what happens? So, remember, you start with the same initial condition, right. Initially, what is the problem formulation? We started with a formulation considering my current initial state. Okay, there is no variation about that. I mean, that is also possible, by the way. Okay, the x naught need not be fixed. Okay, but I am confining myself right now to a class of problems for which x naught is fixed. Okay, if something is fixed, there is no variation of that. Okay, right? Something is fixed, there is no variation. So, because of that, you talk about delta x naught is nothing but 0. Right? So, what you are left out with? You are left out with this term, okay, and you are left out with that term. Remember, this is only one term in the entire series, the only one term. The rest of the terms we have already done it, and this one we do not want to do anything. So, now you put it back. You go back to this equation and put it back. These expressions, whatever expression, delta phi, this one, delta h, this one keep as it is, and this one we just derived. Put it yourself. Put it yourself and then try doing. See, if you derive it once yourself, you will have lot of confidence actually. That's why. You got the idea, right? We have just done it. Essentially, this is all the terms we have done it term by term. This term, this one, that term, this one don't do it anything, just leave it, and this one we have just done it, this one. Okay. So, put all the terms together and start analyzing delta j bar, what you get. And also remember, A transpose B is equal to B transpose A when A and B are scalars, A and B are vectors, okay, of same dimension. A and B are vectors of same dimension, A transpose B is a scalar. So, A transpose, scalar of transpose is same. So, the A transpose B is B transpose A. Somewhere you may be able to use that also basically for collecting terms. Once you substitute all these things back in here, then you collect the relevant terms together, start to group it now. Okay. So, this is what will happen there. You put it everything like that, okay. Then you think, okay, well, I have got a delta x f here, delta x f here. So, I can take common out of that, and I have got something like a delta x here within the integral itself. So, I can take common in that, and this is also delta transpose lambda, I mean delta lambda transpose. So, I can take common there also basically, right. So, you start to group it basically, because remember these are all variations basically. Okay. So, once you have this variation, you can combine like that, and what is the necessary condition of optimality? First variation should be 0. Okay. And what is the fundamental theorem that we talked about? If it happens for all possible variations, the only way it can happen is coefficients go to 0. Okay. Do you see that connection? If it happens for all, see, remember these are all independent variations, right? Delta x, delta u and delta lambda are typically independent variables, independent variations basically. Okay. So, if it happens for independent variations like that, then the only way it can happen is the coefficients go to 0 basically. So, that means you will get some conditions out of this, all sort of things. What does it give you? The first condition gives you lambda f is something equal to that, second one is this one, third one is that one, like that it will get. So, what are the conditions? You get first condition x dot equal to this fellow, right? You get it from somewhere here. Okay. X dot is del s by del lambda. What is del s by del lambda, by the way? What is h? L plus lambda transpose f. So, what is del s by del lambda? H is nothing but L plus lambda transpose f, right? This fellow, this part. So, what is del s by del f? Del s by del lambda f, right? Del s by del lambda is nothing but f actually, right? What you get actually? Sir, here. Is it little bit hot this room now? I think something has to be done. I don't know whatever. Maybe you can open the doors, or I don't know whatever it is. It or is not working or something. What is it? This one is also loud. I don't know. If it is doing something, right, you can do that. I don't know whatever. Okay. All right. Fine. Everybody got into business basically, right? Now, anyway, so let us not distract. So, this is what you are getting here, right? You get all these coefficients 0. So, what you get? X dot equal to del s by del lambda, and del s by del lambda is nothing but f. So, x dot equal to f of x u. That is your state equation to begin with anyway. Okay. And then you get lambda dot is minus del s by del x, and then you del s by del u equal to 0, and lambda f equal to that fellow basically. So, that is why you get all these conditions basically. Okay. All right. So, what it tells you is, if my controller has to be a good solution or admissible valid solution which will solve my problem of optimal control, then it should satisfy all these conditions basically. Okay. What you see here, these conditions. So, remember the dimension of lambda comes from dimension of f. Remember, Hamiltonian is also scalar. So, dimension of lambda is also dimension of f. So, how much is the dimension of lambda? N. Okay. So, that means what you get here, there is a 2n set of differential equations, right? It is not n anymore. N comes from here and n comes from here. So, 2n set of differential equation you have. Is it a big deal nowadays? You have 10 equations or 20 equations, does not matter so much actually, right? Yes or no? Okay. So, but anyway, so you think about that, and then you have got optimal control equation. Is it these two are actually state equation and some sort of a differential equation, right? First two equations are some sort of a differential equation. What is the third equation? Remember, Hamiltonian has no derivative terms, right? So, the partial derivative Hamiltonian will also not have any derivative term. That means simply it is a static equation. It is just a kind of a algebraic equation basically. Okay. So, you solve this algebraic equation for control, and control will become a function of state and co-state both. Remember, Hamiltonian is a function of state, co-state and control everything. So, you solve this equation, control will become a function of state and co-state. Right. So, if you have, but so that is why you need this co-state. Even without that you cannot do it really. Okay. Now, what is the problem then? Is it over? It is not really. The problem is really beginning basically. What you see here? My state equation has a boundary condition. Okay. My co-state equation also has a boundary condition. So, that means even though it is a dual problem, 2n differential equation, can you just stop it? This one you can do it later. Just finish it off actually that way. Okay. Just look at it, what is going on here. This is a critical thing going on actually. Okay. So, this is see, there are 2n differential equations, okay, and you do have 2n boundary conditions for sure, right? Lambda is n dimension, you have got a final boundary condition, right, and you have got an initial boundary condition. So, even though there is the problem begins from here basically. It is not the dimensionality of the problem, that is not a big deal nowadays at least, but the fact of the matter is all your boundary conditions are not given at the same time. Okay. Some things are known here, some things are known there. So, even though I have got my Runge-Kutta method or whatever that numerical method that I am talking about, I cannot really do one shot computation. I cannot just start it and march forward or start there and march backward. Is it, right? It is possible to interpret these two as coupled equations, right? These are in fact coupled equations, okay? Because u is a function of lambda, lambda you put it here, these two are coupled equations, right? So, even though they are coupled equations and boundary conditions are available, I just cannot numerically integrate backwards or forward one time, right? Half of it is available here, half of it is available here, okay? So, that means you have to find a solution somehow which will make it compatible. Obviously, it will require lot of iterative solutions basically, okay? Because immediately you will not be able to know. So, you have to guess something, go there, find out some error, come back and correct and all sort of things. So, that is the reason why this is a problem, this problem is difficult. In fact, this is the reason why it is called 2-point boundary value problem. There are 2 points, right? Some things are given at T naught and some things are given at T f. Okay? So, essentially this is called 2-point boundary value problem basically. Okay? So, all these things are given here, and interestingly, okay, there are many interesting intuitions actually. See this, it is always like kind of, I call that as problem of roommates. How many of you are roommates here by any chance? Hostel roommates? Many times you get along, but many other times you will typically oppose each other. Arguments basically, right? Any topic, you take any other topic, okay, they will tell, oh, this teacher is very good, immediately the next fellow, oh, what are you talking actually? Okay, right? Okay, right? So, and political issue, talk about that, similar things actually, okay. Eventually they may converge, but there will be a lot of debates before that basically, okay. So, anyway, so these are the things. So, in other words, if you see this equation is stable, this becomes unstable and vice versa, okay. What is the difficulty of unstable differential equations? If you talk about a differential equation unstable, the associated numerical integration cannot be done in forward manner. If you do it forward, you can do it, but any inaccuracy of the integration process will going to blow up very soon, okay. If your initial condition is not accurate, a little bit error there, now unstable differential equation you numerically integrate it forward, then the error blow up will happen. So, you have to respect all that actually. So, tell, okay, if the state equation is stable, I will integrate it forward, but associated co-state equation is unstable. So, rather I do backward integration, and which is possible because the boundary conditions are given like that, right. So, if you talk about optimal control design for a stable nonlinear system, it becomes much more easier than an unstable equation, unstable system. The reason being, if it is unstable, my initial condition is given, my final condition of state is not given. I am stuck with that fact, right. My initial condition of state is given. So, I have to integrate the state equation forward. So, I better have a stable system dynamics. But does it make any sense? I mean, why for you talk about control theory, big things, when you cannot control an unstable plant? All that we need is controllability, not stability, okay. As control design person, you should always remember, as long as controllability is there, we will be able to control, okay. So, what is the next thing to do that? There are many other ideas there actually. You split the control in two parts and things like that, and talk about E equal to E1 plus U2. E1 you design in such a manner that it becomes a stable plant, and then U2 you design based on optimality, and finally it will talk about designing the optimal control for a stable plant, okay. That is what the LC operates, by the way, okay. You got all unstable aircrafts pilots cannot fly, okay. So, they have to make some sort of a part of the command inherently generated, which will make the system dynamics stable. I think probably Vijay Patel might have told you in first lecture, right. The first lecture they talk about that actually. There is the control pilot input is not given as it is, okay. There is a equivalent kx part of it, which is automatically generated in the flight computer, which will make the system stable, and then you track it, whatever it is actually, okay. All right. So, this is what it is. So, these are all written down here. If one is stable, the other turns out to be unstable, and essentially this is a stationary equation or static equation. If you solve it, you get it, but while solving it, it is a function of lambda as well. So, you need to solve these two equations together, and it turns out to be a 2-point boundary value problem, which requires lot of iterative solution. And now you start to have a feeling that no matter how much is your computer technology starts improving, these problems are simply not solvable, okay. These are NP hard, NP complete, that kind of computational difficulty problems actually, okay. So, I will not go to that side of the story, but all these observations essentially lead you to something called curse of complexity, okay. Curse of complexity. So, that means you have got a very nice platform, very good toolbox, you are able to impose all sort of constraints, you are able to put boundary condition, cost function, very nice. You come and get stuck here, tell, okay, how do I solve it? If I do not solve it, it is useless basically, okay. and there is only small subclass of problems for which you will be able to solve it basically. Okay. So, let us talk about very quickly, and before doing that, remember this is curse of complexity.
The co-state equation develops backwards because the boundary condition is provided at that. Right?
Cost, yeah, I will talk about that actually. So, most of the time see there are alternate ideas, Sooting method does not do that, gradient method does that. There are many methods like that actually. Okay. And you are not interested in linear systems, so typically you are stuck with the numerical part actually that way. Okay. Anyway, so this is a more general class of transversality condition what we call. You do not have to start with fixed initial condition, fixed final state and things like that. There are, so this is somewhat at t equal to Tf, this condition has to hold good. That means, if my Tf is fixed but Xf is free, Tf is fixed means delta Tf is 0, I am not getting anything from here, and what I am done with lambda has to be what we derived just like that. What about the condition that Tf is free, Xf is fixed? My final point is fixed, I do not care about my Tf, my terrorist hideout is known to me. So, I have to go to x equal to Xf only basically. Okay. I do not really mind whether I go 1 second earlier or 1 second later, how does it matter? Does not really matter so much actually, right. So, I will rather pose that problem that way, like Tf is free but Xf is fixed. Then you go back to that and suddenly this is not valid, what is valid is this condition now. So, Hamiltonian at t equal to Tf should be equal to that fellow. Okay. So, whatever are the missing boundary conditions or missing information, you can get it from this general transversality condition basically. Okay. And t equal to t naught also is valid by the way, similar thing. If you t naught x naught, that combination we started with some assumption, right. Instead of putting xf, tf you put t naught. Okay. In fact, it is some sort of a integral sense, right, integral t naught to tf. So, that means this one all evaluated at tf minus that one all evaluated at t0 has to be 0, that kind of thing. Okay. So, we will talk when those are interested, you can see more on that actually. Okay. Now, before going further, let us quickly talk about a toy example. This is a small example, x1 dot x2 dot is something like that. What is this? Linear system, right, linear second order system sort of thing basically that way. And you talk about a cost function something like this. That means, your at t equal to Tf, my x1 should go somewhat close to 5 and x2 should go somewhat close to 2. That is the soft constraint part of it, right, it is not hard constraint. And then my initial time is 0, Tf equal to 2, and I am starting with origin. I am starting from origin. There is a point in the x1 x2 space called 5 and 2. I want to go somewhere 5 and 2 somewhere there around that. Okay, that is the problem actually, and this is the system dynamics given to me. So, the solution process starts with the definition of Hamiltonian. So, definition of Hamiltonian is whatever is appearing here plus lambda transpose f. So, lambda transpose f is what? F is this fellow, right. So, lambda 1 times x2 plus lambda 2 times f2. Okay. Then you put that your co-state equation lambda 1 dot lambda 2 dot all sort of things, then optimal control happens to be what is your del s by del u? Del s by del u, one is u here and then another is lambda 2 here. Okay. So, u plus lambda 2 equal to 0, that means u equal to minus lambda 2. Yes. So, as long as I get my lambda 2, I am done. Now, the question is how quickly you will get lambda 2. Okay. Let us see that part actually, right. As long as I am, remember these are a function of time, that means lambda 2 of t and u of t. U of t is identically equal to negative of lambda 2 of t, that much is very clear. Now, how do you get it? Okay. You put it back and then okay, well my boundary final boundary condition has to come from this. So, this part, right, this is your phi basically, right. So, what is lambda f? Del phi by del xf. So, lambda f is nothing but lambda 2 is this fellow basically, these two, and this is my initial condition. Now, I interpret that as a kind of a dual space problem. So, I will talk about z is nothing but x1 x2 and lambda 1 lambda 2 together basically. So, we talk about if I go back, what is my lambda dot? Lambda dot is this one. Remember, x dot is a linear system, lambda dot is also a linear system. So, I should be able to combine that and interpret that as a coupled state space equation. Okay. So, I go back to that and then tell okay, well this is nothing but my 4 states, and then I can write it in this form actually, right, z dot equal to az, where a is something like this. Looks very simple problem, right. There are so many zeros and a couple of ones, that is all. In the A matrix there are many zeros, right, and couple of 1 minus 1 is appearing, that is all it is actually. So, if you have a linear system like this, what is the solution? Solution is this form, right, e to the power at into c. So, you put it there and then tell okay, what is my c, because a is known to me, a to the power at I can do. What is e to the power at by the way? Laplace inverse of si minus a inverse. So, I can compute that, that is not a problem. So, I do all that and then at t equal to, so you can first you start putting your boundary conditions, very quickly you will realize that C1 C2 is nothing but 0. Okay. You put the boundary conditions here, okay, in this coupled equation, no, whatever there, and then it will turn out that okay, C1 C2 0, but now t equal to Tf equal to 2. So, I go back to this 2 and interpret all that. How many equations are there? 4. How many unknowns are there? 1. How many unknowns? 2. Huh? How many unknowns are there? 4 equations, very clear, right? How many unknowns? 2. 4. Okay, what are the 4? x1 of 2, x2 of 2 and C3, C4. Okay. But it is a linear system after all, right? So, what you have to do? You rearrange the terms and write it in the form of Ax equal to b. Okay. You rearranging the terms, you write that way and solve it that way. Okay. Then you get what you mean, all the things are available to you, and finally you tell, well, my state space and co-state both are available, and because my lambda 2 is now available, my control is that, right? My lambda, what was my control? Control was negative lambda 2, right? So, I not only solve for lambda 2, but I ended up solving the entire state space and co-state both actually. Okay. So, that is how I got it. So, these are all simple linear problems, okay, we can do it something like this. In general, can you do it? Okay. So, that motivates to the second problem. In talk about some sort of a orbit transfer problem, let us say. Your satellite is orbiting in one orbit, both are circular, let us say, most of the time it is elliptical anyway. But circle is a subset, kind of a subset of ellipse, right? When A equal to B, it is a circle. So, it is a circular orbit and you want to take it to another circular orbit. There is a thrust action that you can do, thrust actuation, and finally you can merge it. And this requires some sort of a, see, remember all orbits are typically in a plane. So, even though it happens to be 3D, that is what you look around 3D, right? But if there is a satellite orbit, even moon's orbit, that typically happens in a plane. Okay. That plane itself can be inclined to earth axis, that is a different issue. But the circle is doesn't, it is not a 3D orbit sort of thing, right? It is actually, that keeps on rotating, same thing only, years after years, earth around the sun, what happens? Every 365 you are back to square one actually, right? It happens to same thing again and again actually. Okay. So, this is actually a plane. So, you require 2-dimensional things, u dot and v dot are given something like this, mu is nothing but gm by the way, gm by r square, right, that term, G capital M, that is typically known as mu, and these are the system dynamics. Nonlinear, but is it really untractable? Okay, it is nonlinear, I agree with that, but is it really a very bad nonlinear thing, something like that? I do not think so. This just looks like some 2-3 terms are there, that is all actually, right. Now, let us see what kind of problem you will end up with basically. So, you put that there, your system dynamics becomes r dot is u and u dot v dot is given there. R is radial distance actually, right? R dot is u and u dot v dot are given there basically. Okay. So, with respect to these 3 system dynamics, you have these boundary conditions, right? T equal to T naught, you are in the initial orbit, initial orbital parameters are known to you. T equal to Tf, you exact what point will not be given, only the orbit will be given actually, sort of thing. Okay. So, T equal to Tf, it should satisfy some sort of a equation. Your state variable, whatever variables are there, no, this is initially this orbital parameters, finally that orbital parameters. Okay. So, finally this UVR has to satisfy this orbital parameters, that will be represented by some sort of a equation actually. Okay. So, these conditions have to satisfy there, psi 1 UF has to be 0 because finally it should not go radially, right, it should go tangentially. So, UF has to be 0 and your other equation is VF should be equal to square root of mu by RF. It is a circular orbit, remember that. What is Vf? What is V square by the way, right? V square by R, that term. Can you see, can you correlate that? What is V square by R? Centrifugal force, right? Centripetal acceleration or something that way. So, that is what it is, that is what it happens basically. So, this is how you get your initial condition and your final conditions. Now, let us start with Hamiltonian. Hamiltonian is, what is that Hamiltonian? L plus lambda transpose F, L plus lambda transpose F. So, L is nothing but my RF, right, that has to be maximized. So, I talk about some sort of a maximization of circular orbit, right, that is what the problem. I have got some sort of a thrust actuation capability. I want to actuate it maximum and go as far as possible basically. Okay. That means my RF has to be maximized. My radial distance from center, that is RF, that has to be maximized actually. So, that is how this cost function is like that. So, your H equal to this all these formulas L plus lambda, L is 0 actually by the way here, right. because inside integral nothing there, it will only come in the boundary condition. So, L is 0, lambda transpose f, f is f1, f2, f3, f1, f2, f1, f2, f3. So, your lambda 1, lambda 2, lambda 3, okay. Lambda 1 times f1 it is u, lambda 2 times this one, lambda 3 times that one, okay. You have to put it together. So, this is your Hamiltonian. What is your phi? Phi consists of this condition which is directly comes from here, and then you talk about some sort of a final conditions, and final conditions are equality, then you have to introduce some variables called nu, okay. It is kind of lambda, but lambda is time dependent T naught to Tf, but new variables happens at Tf only, okay. It is a Lagrange multiplier sort of thing. So, you put it there, and then this phi comes out to be like that. So, then you put it something like this, and then well my state equation, co-state equation, optimal control, boundary condition. Remember there is 4 conditions: state equation, co-state equation, optimal control, boundary condition, okay. So, you put it like that, and this turns out to be somewhat like that. So, now can you solve it? These boundary conditions are there, and these are the things. Impossible to solve in closed form. There is no e to the power 80 sort of thing, right? E to the power 80 is just not there. So, you have to talk about numerical solutions and all that. So, that is where this motivation goes towards, can we really solve it numerically, okay. All right. So, that everybody clear on that, okay. All right. So, what you see, all these difficulties, this course of dimensionality, I mean course of complexity. One more thing that we forgot, that okay, you can do all this closed form or numerical, most of the time numerical anyway. You get it, you struggle it and get some solution, but that solution is valid for x naught only. Remember that t equal to t naught, that is the boundary condition, right. That particular solution that you are talking about, after all the struggle back and forth numerical, and see there are classical methods and all, you can go back. I thought I will cover one, but there is no time, so I will just keep it probably, okay. So, there are sorting method, gradient method, there are many approaches actually, okay. You talk about that, and there are multiple sorting, there are transcription method, there are many things there actually, okay. So, we will not talk about that, but having said that, all that bottom line is, at the end of the day I am getting solution from a particular initial condition, okay. That means whatever I am getting u of t, t naught to Tf, what is that? The solution is open loop, right. The moment my x naught is not my x naught, something else, that x of t naught is not my x naught, something else, then the entire solution is meaningless actually. You just operate something, I mean if the controller has robustness it will work, but certainly there is no meaning of optimality, right. So, in other words, for every x naught we need to have control solutions there actually, right, yes or no. One snake itself is difficult to handle, now you talk about millions of snakes actually, okay, like that kind of a thing. So, you got many x naught, right. How many x naughts are possible in a domain? Infinite, okay. That means you really need to talk about some sort of a feedback solution. Does it really happen or not happen, okay. In other words, if my x naught changes, my control should be ready as a function of x naught, right. Entire control history should be as a function of x naught. Is it possible or not possible? So, that concept is called, that philosophy has been developed, and that is called dynamic programming. We will see a little bit of that also basically, okay. So, all right, the numerical methods I am skipping, okay. By the way, I got NPTEL lectures and all, those of you are interested you can study, that is not a problem actually, okay. But so idea here is, we have got so much of exercise, end of the day we got this 2-point boundary value problem, and that happened to be course of complexity, and we have got numerical methods, but after all that you are getting is open loop solution, okay. Now, can you make it closed form, closed loop basically, okay. So, that idea is called, this Hamilton, Jacobi, Bellman has proposed all that, it's called dynamic programming, dynamic optimization again, okay. It starts with a very standard motivation, it is just to obtain state feedback optimal control, not open loop, but feedback. Remember this LQR and all that, you always talk about E equal to minus kx, right. It is a feedback form, ultimately that was the ambition. Can you really write it as feedback form, okay. So, how many of, I mean this entire philosophy relies on with a very standard logic, which talks about something like a very standard, which makes some sense actually, right. How many of you eat fish? Just to make it, okay. The claim here is, if a fish is tasty, then any part of the fish is tasty, good. Does not make sense, okay. Really not, okay, okay. But that is what it is, that it tells you like that. which talks about any part of an optimal trajectory is optimal trajectory. Okay. And it can be shown in 2 seconds actually. All that it tells you is, if I got an optimal path like that, I cannot have a part of the optimal path as something better than that. It is just not possible, because if this part is better than that path, then the integral is nothing but is a to c plus c to b. So, this a to c path, if it is not optimal, something better is possible, then I could have taken that path rather, right. That means, this path would have been a better optimal path. That means, my original claim is not good. Original claim I told that this path a to b via c, this solid line is the optimal path, and if that is not optimal, a segment of that is better than that, then that segment is something that I should have followed. Okay. And hence, that claim is what it tells you, any part of optimal trajectory is optimal trajectory. Right. You take already there is an optimal trajectory, you consider any segment, that by itself is also optimal basically. So, if you rely on that philosophy, okay, and you can very clearly revisit this problem, and now you talk about a constraint set also, and then you will talk about something like, well, I will not go through the theory becomes again too much of a math sort of thing. It talks about, okay, I will have some sort of a optimal cost, and optimal cost is, okay, T naught to T naught plus delta T, and a T naught plus delta T to T f. I go one baby step delta T, and consider the split this integral into 2 parts. So, this part T naught to T naught plus delta T, and T naught plus delta T to T f, and then this part is something that I will define as something like this J naught, this part is something like again optimal V basically. So, what it tells you is, okay, once I define this part I can write it as something like this fellow, right. This is like trapezoidal rule of integration and the 1 delta T integration, right. Integration is one stripe is something that you are doing actually, right. So, quadrilateral, see, if you have some sort of integration of a function, what you have to do? You want to have some integration of some function, right, and this segment, okay, what you have to do? Well, this is not a good example, I will talk about this segment rather, okay. What talks about, okay, there exists some value somewhere in between these two, so that this area under this curve is actually the area under that, right. If I talk about area under this curve, there exists a point, I evaluate the function value there within the interval, and then I take the quadrilateral area, then the area is same as the actual area basically. Okay. So, that is why this alpha and all the things are introduced there, and you talk about that. Then the next one is expanded using Taylor series. Okay. So, you do all sort of algebra, and then finally, what you will end up with is you define your lambda as something like del v by del x. Now, somebody was asking like that, what is the meaning of lambda? The meaning of lambda happens to be sensitivity of optimal cost with respect to state, that is comes to that actually. Okay. And then you once you define that, it satisfies this kind of a equation. Now, what you have it here? Remember, this lambda is optimal lambda actually. V is different from J, right. This is J, then you introduce this term V is optimal J. Okay. So, the lambda associated with del V by del x, not del J by del x. Okay. That means, lambda is nothing but sensitivity of optimal cost with respect to the current state basically. So, that is that kind of interpretation, and you will end up with something like this. What kind of equation is this? If you solve this equation, you are done by the way. Okay. If you solve this equation for u, then u will be a function of state and co-state, all sort of things actually, closed form solution will get it anyway. Okay. Yes. So, what kind of equation is this basically? Okay. If you just look at it, this equation happens to be, what is lambda? Lambda is this fellow, right, del v by del x, you put it here. Lambda is not lambda anymore, lambda is del v by del x. You interpret this as a some sort of equation for V, right. V is your optimal cost actually, right. So, what kind of equation is this? Nonlinear partial coupled differential equation, right. Nonlinear coupled PDE, not ODE anymore. Okay. Nonlinear and coupled PDE now. Okay. So, can you really solve it in closed form? If you solve it in closed form, you are done, because the moment you know V as a function of x, then lambda is, you know that, and control is immediately a function of state and lambda basically, right. So, we will get control as a function of state basically. Okay. So, now can you do that? Can you know that? And it turns out to be impossible actually. Okay. So, but having said that, this equation what you see here, del v by del t plus h out equal to 0 is nothing but something called HJV equation.
Coupling in that equation, where is the coupling coming from? Where is the coupling seen?
The PDE, so this V is a function of time, V is a function of state, V is a function of co-state, all that, and state and co-states are related actually. Lambda dot is a function of other things basically. Okay.
That is because
Well, okay. I will take back my word, because you see, if you interpret that way, if you interpret for V, V is a scalar anyway. So, V is a scalar, then it is not coupled anyway. Okay. So, it is only a PD, that sense, non-linear PD, you can say that way. Okay. Because V is not a V1, V2 sort of thing, V is single V. So, that is why it is okay, you can interpret that way basically. So, V is actually a non-linear PD. Okay. Can you really solve it? It turns out to be impossible again basically. Okay. Now, for that for small problems you can certainly do that. Now, let us talk about an example sort of thing, but before that, this is the summary. You define what is V and put it through this equation del V by del T plus H of t equal to 0, and that whatever solution you get, that is nothing but your state feedback optimal control actually. And before that, there are some observations, that if your domain happens to be infinite, that means control is not constrained, then you can use this del S by del E equal to 0. Otherwise, you have to minimize the Hamiltonian within the constraint set, right. The moment constraint kicks in, this del S by del U need not be 0, but if there is no constraint, then del S by del E equal to 0, that is that you can keep it. And then if you have this see, this is something like TF to TF, that means V of TF XF, you need some boundary condition associated with that, right. So, that V of TF XF happens to be 0, because TF to TF actually, right. But if your V happens to J contains that, because initially, okay, I am skipping, some of these things are very rapidly going. So, just tolerate me a little bit. So, we started with some function like this, right, there was no phi. So, when t equal to TF, this is TF to TF, this is 0, okay. But when there is a phi, that phi is left out basically, right. So, that one will appear basically, okay. So, you talk about V of TF XF is nothing but phi basically. And also turns out, if you talk about infinite time problem, TF goes to infinity, like your Riccati equation, those of you know that TF goes to infinity, the algebraic Riccati equation happens, right, differential Riccati equation to algebraic Riccati equation, that kind of thing. So, if eventually even here, when TF goes to infinity, you can show that del V by del T happens to be 0. So, that means this equation what you have, if it happens to be a scalar problem, if your state is single, then this PD will turn out to be ODE, right. This is a partial differential equation in n plus 1 variables, right, x1, x2 up to xn and then t. Okay. So, if you have got only one state and t part is not there, this is not there, then you have got partial differentials all in terms of x only, that means it is ODE basically. Okay. So, that is the class of example that we are going to talk about now, and let us do that actually. Okay. Just take your pen and paper again. Just talk about J is like that, subject to something like this. Remember, this is a scalar, but a nonlinear equation, and in fact, this has happened to be a standard benchmark problem actually. Standard benchmark scalar example problem. What is good part of it and all? Minus x cube is a stabilizing term, right. X is a destabilizing term, but minus x cube is a stabilizing term. We can show that in Lyapunov theory 2 seconds actually. So, that means if you use feedback linearization, you lose beneficial nonlinearity, right. What you will do, if you just do feedback linearization, what do you do? U equal to x cube minus 2x, let us say you put it that way, x cube minus 2x, right. So, x dot equal to minus x, that will become stable. Okay. But at the end, of the day, what you have done? You have cancelled the beneficial nonlinearity, which is not good. Okay. So, do not want to do that, just do it yourself, do not tell yes, just stop doing. Okay. Just start putting, I mean the steps are there. So, J is like that and your state equation is like that. So, what is your Hamiltonian? L plus lambda transpose F. So, that is what it is, and what is the condition? That is not okay, it is infinite time, TF goes to infinity, right. So, del V by del T is 0, okay, and it is got this non constraint, this control is not. So, that means del S by del E equal to 0 you can use. Okay. So, if you use that, what you get? U equal to minus lambda. Okay. So, your H opt, so this is H and H opt is optimal Hamiltonian. So, you put that U equal to minus lambda here and see what is your optimal Hamiltonian. Okay. Now, what does the condition tell you? Del V by del T plus H opt equal to 0, this is the condition, right. Del V by del T plus H opt equal to 0, del V by del T is already 0 and H opt is the one that I am talking about. Now, I will make it equal to 0. Okay. What is lambda by the way? Del V by del x, right. But you do not want to solve for V, that is the mistake that people do many times. Okay. You do not need a solution for V. What you need a solution for lambda, and this is already an algebraic equation, right. H opt equal to 0, just put equal to 0 and solve for lambda in terms of x. It is a quadratic function of lambda, right. Just solve for lambda in terms of x. H opt equal to 0, it is a quadratic function of lambda, solve for lambda. Then u is nothing but minus lambda, that is as simple as that. Okay. So, lambda is a function of state and hence u minus lambda is also a function of state. Yes. Now, the question is ambiguity, you have got plus or minus term, right. Okay. How to eliminate that? Okay. One, in fact, one will be stabilizing, one will be destabilizing. By mistake you use the other one, you are gone actually. Okay. There is a plus or minus term, right. So, you have to resolve that ambiguity actually. Done everybody? It is just minus b plus or minus b square minus 4ac square root all that actually, right, that can by 2a. All right. So, this is what it is. So, you put it like that, a lambda happens to be like that. Now, the claim here is you take your lambda to be like this, okay, but out of this u, this fellow I will select, minus the minus term I will select, not the plus one. Plus I will not select, I will select minus, and this happens to be stabilizing. Okay. You can show that in using this Lyapunov function, standard Lyapunov function. They take half x square, then what is v dot? X times x dot. So, x times x dot is nothing but that, and that happens to be in this form actually. Okay. And this one is locally positive negative definite certainly, right. 1 minus x square term is there, right, something whole square is there. So, this term is positive guaranteed no matter whatever is the value, 1 minus x square whole square is positive, right. So, positive positive square root positive with minus term and all that actually. So, if you take that controller, it is not local, it is actually global in that sense, because this is actually negative definite, right, throughout. Okay. So, this controller what you get is not only optimal, but is also stabilizing globally. Okay. That is the powerful thing that you talk about in optimal control. Not only you get an optimization idea, but you will also get stability along with that. Okay. And can you ever think about this formula without optimal control theory? Can somebody, okay, no feedback linearization, backstepping, nothing will give you this, right. Can you think about this formula otherwise? Okay. It has become a benchmark problem. Any time you want to propose a new numerical technique or method or whatever it is, you can actually compare the solution with respect to the solution. In fact, one of our papers and all, we talked about that also basically. Okay. All right. So, what are the facts? The facts are dynamic programming is a very powerful technique in the sense that if you are able to solve this HIV equation, you have got a state feedback optimal control, very big claim. Okay. And then HIV equations happens to be both necessary and sufficient. See, in the other approach we only talked about necessary condition optimality, right, state equation, co-state equation, all sort of things. This happens to be necessary only, sufficiency condition we did not even talk about actually. Okay. Here we do not have to worry about that, if both of that will be satisfied together. Then at least one of the solution is guaranteed to be stabilizing. Remember the example we got two solutions, right, one was plus, one was minus and all that, but at least if you have multiple solutions like that, at least one of that will be guaranteed to be stabilizing basically. Okay. So, you select that and you are done basically. Okay. So, what are the problems then? So far so good, but problems are in general the resulting PD is very difficult to solve. I mean this is tiny toy lollipop problems are okay, but the moment you go to orbit transfer and all it is impossible.
This HJP gave you a closed loop solution. Is that because of HJP, using HJP, or is it because you have freed up the final state?
Which one?
Earlier, you came to HJP because in the previous situation you had an open loop solution, and so you said now if you go to HJP you will have a closed loop solution, right? But is it because of the HJP you got a closed loop solution, or because along with actually introducing HJP you also freed up the final state?
Yeah, you have to see in general you will not be able to get, in general you will not be able to solve, but if you are able to solve then you will get again closed form solution anyway.
There is a free final state problem, whether you use HJP or not, will give you a closed loop solution, right?
It is not really free final state. I will say that we see what has happened here is there are two things actually. One is TF goes to infinity, Okay, that is the first condition, and then the control is unbounded. Controls,
You don't
see,
have a constraint on XTF.
you don't actually.
Yeah, but there you had a constraint on XTF.
Okay, all right. So that is okay. If you put that, then this problem will
Once
be.
you have a constraint on XTF, it's closed, it's open loop.
Well, this condition will come V of Tf. So now you cannot get away by solving this fellow only lambda. You have to solve for V rather. Okay. So you see the bottom line here. You would never bothered for solving for V here, right? We just lambda. Lambda is del V by del x. So del V by del x was sufficient information for us here. But if you have a boundary condition for state also, then you have to solve for V. Then only you can talk about getting it extracted from there. Okay. All right. So these are the things. So what you see here, even though it's also very good, very appealing and things like that, you are getting caught with this kind of things basically, right? Resulting PDE solution is very, very difficult, and there are numerical techniques also available for solving this HJV equation. But then that is a tree structure. That means it is exponentially growing. Okay. That means what it tells you is it is numerical techniques are extremely difficult either. So what it tells you is if the problem duration is longer, like TF to T0, T0 to TF is longer, or the dimensionality is larger, that means I have got state dimensions higher, then the solution is not possible actually, because it is exponential growth is there, the complexity part of it. Okay. So this is what the Bellman himself realized it, and then he told something called curse of dimensionality. Okay. What was the other one? First one, curse of complexity or curse of dimensionality. Okay. So you are caught either way. You are either like devil or deep sea, they call, right? One side devil, one side deep sea. Basically, so where to go basically that way. All right. So more of that, you can read some of these books and all that. One of that, I put my thing also, but it's not ready yet. Okay, it will come in another 1 or 2 years basically. Okay. But that is, well, other things are there, and then you can read some of that and then get ready for that actually. But then that actually ends the first lecture. We will go to the second one now, and some of these references are for your numerical techniques and things like that actually. Okay.